In the last project, we are going to solve a maze. This is a maze, okay? A labyrinth. This is a maze. So we are going to try to solve one of these. Okay, there are several algorithms to solve mazes. One of them, the first one, the most simple one, is the random mouse algorithm. The random mouse algorithm I'm going to show you in just a bit. Okay. In this one, in this trivial method that can be implemented with a very unintelligent robot or perhaps a mouse, it is simply to proceed following the current passage until a junction is reached, and then to make a random decision about the direction to follow. Okay? Although such method would always eventually find the right solution, this algorithm can be extremely slow, as you can see here. The robot is going to find out the solution, but eventually. It's not very efficient. Okay? You can implement this one, but well, it's not going to be very well evaluated. Okay? So we have here the first one. The mouse, as you can see, the random mouse algorithm. Okay, the second one is the wall follower. Okay, the wall follower is, as you can see here, we have a right-hand rule. Our robot is following a wall and always turning to the right. Here it can turn to the right, so it turns to the left, but here turn to the right, and it's always turning to the right. It following the wall, okay? And at the end, eventually, it's going to find out the solution here, okay? The end of the passage, okay? The wall follower, the best known rule for traversing mazes, is also known as either the left-hand rule, because you can use the left-hand rule. Also, you only can turn only to the left, or you have also, as I told you, the right-hand rule. If the maze is simply connected, that is, all its walls are connected together or to the maze outer boundary, then by keeping one hand in contact with one wall of the maze, the solver is guaranteed not to get lost and will reach a different exit if there is one. Otherwise, he or she will return to the entrance having traversed every corridor next to that connected sections of walls at least once. So I'm going to show you one wall following robot that is here. Okay. So another perspective into why wall following works is topological. If the walls are connected, then they may be deformed into a loop or circle. The wall following reduced to walking around a circle from start to finish. To further this idea, notice that by grouping together connected components of the maze walls, the boundaries between these are precisely the solutions, even if there is more than one solution. You can see here this wall follower solution. Okay? So, if the maze is not simply connected, this method will not reach the goal. So we have to be careful with this method. Wall following can be done in 3D or higher dimensional mazes if its higher dimensional passes can be projected onto the two-dimensional plane in a deterministic manner. Okay, this is another way to solve a maze, and you can think about how to do this with the things I told you before here. Okay. So. Okay.
The pledge algorithm is a maze traversing algorithm used when the walls are disjointed. The robot keeps the obstacle either on its left or right hand side and keeps track of all turns using a counter. Increment the counter and left turns decrement the counter. When the counter reaches 0, the robot has traversed the obstacle and it continues on its pathway towards the beacon. Let's look at some examples of the pledge algorithm in action. Similar to the first example, we put an obstacle in its direct pathway. The robot moves towards the beacon but now hits the obstacle, so it'll enter the pledge algorithm. It will try to follow the obstacle on its right hand side, so that means it will be turning left first. Left turns decrement the counter, and right turns increment the counter, so we will see that the counter will be decremented. It moves forward one block, and now will be turning right. Since the robot is doing a right turn, the counter will be incremented to 0. The robot will move forward one more block, and now that the counter is 0, it has traversed the obstacle, and now it will continue on its pathway to the beacon since it has left the pledge algorithm. I'll briefly go over how the code works for the pledge algorithm. For the right-hand side algorithm, the robot always begins by turning left. For every movement, the robot will check the front, left, and right obstacle sensors and perform the following logic. If there's no obstacle on its right, it'll move in that direction. If there is an obstacle on its right, but no obstacle in front, it'll move forward one block. If there are obstacles on its right and in front, it'll turn left. The robot will continue this logic at every step, counting each turn until the counter reaches 0 again. Let's look at a more complicated example so we can understand the code more clearly. In this example, we've placed more obstacles to see how the robot will react. The robot will begin by hitting the first obstacle. The robot will enter the right-hand side pledge algorithm, meaning it'll try to keep the obstacle on its right-hand side, so it'll begin by turning left. This decrements the counter to -1. When the robot checks its obstacle sensors, it sees there's an obstacle on its right and also in front, making the robot turn left, and which also decrements the counter to -2. When the robot checks its obstacle sensors, it sees there's an obstacle on its right but none in front, making the robot move forward one block. There is no obstacle on its right, so the robot will move in that direction, which will also increment the counter to -1. The robot checks its obstacle sensors and sees there's an obstacle on its right but none in front, so it'll move forward one block. Same as the previous square, there's an obstacle on its right but none in front, making the robot move forward one block. So now the robot sees there's no obstacle on its right, so it will turn right and move forward in that direction one more block, which increments the counter to 0. So now the robot sees that its counter is 0, so it leaves the pledge algorithm and has successfully completed the pledge algorithm, so it will continue on its pathway towards the beacon. Note that in this tutorial, the right-hand side algorithm was described. For the left-hand side algorithm, all right turns are left turns instead, and vice versa. The robot will decide whether to do a right-hand side or a left-hand side, depending on the scenario. You may be asking yourself what happens when the robot has completed the pledge algorithm since the counter is 0, but there's still an obstacle in front of it. Now if we take our previous example, let's say we put an obstacle in front of it. Now that there's an obstacle in front of it, the robot cannot go forward towards the beacon like it would otherwise try to. So now what would it do in this case? it would actually re-enter the pledge algorithm and it would try to traverse the obstacle like it previously did. That concludes this tutorial about the pledge algorithm. I hope you enjoyed it, and thank you for watching. In
Okay,
this tutorial, we'll be going
to help you do that, I'm going to show you one function that you don't know and it's going to help you either in this project and either in the previous one. So we can use one of the functions in the robot library that is called turn, okay? And this turn make the robot turn a certain number of degrees from its current orientation. The current position is derived from the onboard compass. We've already used the compass, so we can use this function to perform better our program. So the syntax is going to be robot.turn between the brackets degrees. So the degrees can be from minus 180 to 180. Okay, so we can go from a left side to the right side. Okay, and we have here, you can check this in the Arduino.ctc webpage, and you have here one example. For example, robot.turn 90. Make the robot turn 90 degrees right from the position it currently has. Okay, so this is going to help you perform your programs. You can also check more functions you have in the Arduino webpage that maybe can help you perform better your programs. Okay. Then we can use, but this is more difficult to implement, is the Tremox algorithm. Okay, I'm going to show you how this algorithm works. This algorithm implies to draw a line on the floor. So it's difficult for us, but if you can do that, you are going to have a very good degree. Maybe you can set, I don't know, a kind of painter in your robot that is painting the floor, and with the infrared sensors we can, as we were doing the following line robot, maybe we can check that we've already passed through that passage. But this method is going to be really difficult for us to implement because it's difficult for us to paint the floor. So it's up to you to do it or not, but it's another algorithm we can use. Okay. We are going to watch now what is another strategy. Maybe it's not going to be very good for us, but I'm going to comment it. Okay. So this is the dead end strategy. The dead end filling. Okay. So you can see here in a pretty quick way, there is an algorithm for solving mazes that fills all dead ends, leaving only the correct ways to leave the maze and fill. It can be used for solving mazes on paper or without a computer program, or with a computer program, but it's not useful to a person inside an unknown maze, since this method looks at the entire maze at once. So it's not suited for us. Okay, we can use this solving method. So I'm going to show you the recursive method, that is a way that maybe we can use. Okay. Okay. Yes, this one. So now.
Hello everyone, and welcome to traversing through a maze in this 3-minute tutorial we're using recursion. So right here on the left side, as we can see it, we have the pseudocode to going through this map. Assuming we're at this coordinate right here, the beginning, where the star begins. Let's assume that's coordinates 5, 5, and the user always puts that in, or the program always puts that in. So we don't need to use error checking right here. Let's figure that out. And if we didn't have that guarantee, then we'll have to error check. But anyway, starting from here, we start going through the pseudocode, right? So from this current location where we're at, 5, 5, is it the marked as the exit? No, it's actually the entrance of the maze. So we skip this if statement, we go to the else statement. Now in this else statement, we're basically checking down from the current position, so this place right here, left, up, and right. So we start with this very first one, down, right? When we check this down, it's not marked, it's not a wall, so we move over here. So basically this code right here sets current position to down from the current position, so this 5, 5 becomes 5, 4, and then we mark it. So let's use C to basically say that we cleared it, or it's been covered. Alright, and then we move to this statement, which recursively calls the function again. So we open this function, except now we're using this new location. So we're calling the function from this spot right here. Again, it's not the exit, but it is down. Down is clear, it's not a wall. So we go over here. Same thing exactly happens, we move to over here. Now, when we go through this, is it the exit? No. Down, is it marked? No, but it's a wall. So it does not run this if statement. It goes on to this one. Left is a wall. Top is marked already. We marked it with a C. And then to the right is a wall. So we exit this recursion, we go back to continue the other one. Remember, we left off right here when we called recursion to get to this place, or rather to run it from here. So we go to this if statement, right? Is it left a wall? Yes. Top wall? No, but it's marked. Right is wall. So we move back to this one. Same checks. This one is marked. Everything, and then we basically move on to checking the left. It's a wall, top is a wall, right is not a wall, it's unmarked. So we move over here and we mark it. So that's essentially how the recursion works in this, and basically it keeps going, right? So once you get here, we check bottom, and then bottom is clear, bottom is clear, bottom is clear. So basically you're going to go all the way down here. And then recursively you're going to check, it's a wall, so you're going to go to the left, right, up, and then you're finally going to go to the right, and it's not going to work, so you're basically going to backtrack all of this, go all the way up to this, you're going to start going to the left. So now you see how it works, right? Well, if you need any more help, I mean, this is a very short tutorial, just go to type in maze solving algorithm into Wikipedia and you get this pseudocode. It's a little bit differently, but basically it works with this double array, which is basically what we're doing. And yeah, I hope it helps. Thank you very much. Have a good day.
So this is not. This is also not very suitable for us because, as you can see, you need to kind of write in the maze. So we are not going to do that. So this also is not very suitable for us. Okay. You also can, if you check the web, you can also find maze routing algorithm. You have here also another method we can use. The shortest path algorithm, this is not suitable for us because we need to know previously the complete maze, so it's not very suitable for us. So the better ones, we have here the recursive algorithm, this is the one that we've already seen. The better one for us is going to be the pledge algorithm, the wall follower, and the random mouse algorithm. So check the different methods, or you want to use your own method, it's going to be much better. Check your method and solve any maze you want. You can build one maze, okay, whatever you want. You can put some walls with I don't know, with some cases, or with whatever you want, with whatever obstacles you find, and build a small maze and try to solve it. Maybe this is going to be the best one for you to use, the wall follower. Okay, so now you have your last project. Okay, good luck, guys.